Ellie, good morning. Hello, Anne-Sophie. Good morning. Glad you're both there. Teresa's there too. Good morning, Teresa. Gotcha. Thank you, Anne-Sophie. Okay, I think I have 4. Let's see if Zach is there too. Okay, well, while we're waiting for Zach, I'm going to go ahead and get something out, which is my earthquake sheet. Okay, so you may have the same thing if you ran it off or just did the questions. And it's due, I forget, today or tomorrow for you. And I want to see on 1A through F if you have any questions about it, how to do it, what they're asking. So if you have earthquake questions now, don't tremble, just ask me. So how's it going? Anything you'd like to ask about with earthquakes? I'll get this focused not on me, but on the screen, which is more important than me anyway. All right. Going okay? Not going okay? Haven't looked at it? Please look at it. So it may not take you that long, but there's a few little calculations you got to do. Nothing huge. Okay. Okay. Thank you, Ellie. All right. So I'll assume that the others don't have questions either, and I hope Zach shows up, but we're going to go ahead and start for the day. Maybe Zach's there and can't respond because I see 4 people out there, but never figured out if one of those is me or not. Okay, if we're all right with that, then let's go ahead and go back. What we're going to talk about today are applications of refraction, okay? So refraction, let's kind of warm up our brains, okay? Refraction was when a wave changes. Refraction is a wave changes. What is changing when we have refraction? And today we'll mainly talk about, we'll do actually sound and light and some applications of refraction. Thank you, Ellie. So we're changing medium. We're going, for example, the one we did yesterday was air and water for light, but you could have other stuff too. You could have glass and light. You could have glass and water. You could have, I don't know, if you're walking, you could have 2 different things you're walking through. I could be walking on ground, and then I could be walking through tall grass. I know you're not a wave, but it would certainly change once you change your medium, going from flat, level, nothing there to suddenly tall grass that you got to walk through. See what I'm saying? So it changes, in our case, the wave, and it makes the wave bend. So let's review a little bit with one of my favorite characters through the years. Here we go. This is Arga. And Arga is an ancient spear fisherwoman. So here she goes. So the question is where to aim. Okay, so we're going to just draw Arga here with her spear. And here's the water. and it's a deep basin here. Okay, now she sees a fish. So here's where she sees the fish, and I'm going to draw that in green. So I'm going to follow her eye, and I wish in class we could do this, although next week, theoretically, we can do this. I hope I see you in class. Here we go. Here's her eye. Draw a straight line. So she looks straight like this. And this is what she sees as the fish. But I'm going to call that the apparent fish. In other words, it's not really there. Now, how to figure out where the real fish is. Okay, where her line of sight, where she sees the fish, crosses the water, draw a line there. We drew this line yesterday, right? And that's our normal line. And we can extend that underwater too. And we said that you know what, I'm going to make that a solid green line. So she has real rays of light going here. But then that's only the apparent fish. So maybe I should like dash the fish in too. But anyway, that's up to you to be artistic or not about that. But we're going to figure out where the real fish is. What happens to the light once it hits the water? It bends what compared to the normal? Here's the incoming angle. We call that the incident angle, if you remember from yesterday. And when it goes into the water, which way does it bend? It does not go straight. So the dashed line goes straight. Does it go more, I don't know, away from the normal or towards the normal? What does it do when we get into a denser medium? We call the water an optically denser medium. Water, optically denser. So everybody, take a guess. Will the line bend away from the normal or toward the normal? What do you think if it's denser? Thank you. Good. All right. So it bends towards the normal. So the actual fish, you ready? Although it's not important to you and I, it's a hair deeper and it's closer to the normal. So that is exactly right. And I'm going to put that angle in blue. So the angle is going to be called the, well, I'm going to put the fish in first. Here's the fish down here. Maybe it's a happy fish. Doesn't know that Arga is up there waiting for the fish. Okay, so at any rate, so Arga's got to aim not straight, but a little more towards herself and closer in because the wave refracts, as Ellie said, and Teresa as well, that it goes towards the normal. Thank you both. So she's got to aim more in that direction, okay? All right, and that, of course, is called the refracted angle. And to be honest, if you're a fly fisherman or fisherwoman from where I come from in Montana, you do the same thing. You want to go out a bit so you come away so the fish doesn't see you. You actually don't want to be here. You want to be a little further back and then kind of cast over there so the fish does not see the person. Okay, but it's because of refraction to know where to stand. All right, good practical knowledge next time you're fly fishing. I hope it will be soon. Okay, let's see some other cool applications of refraction. I'm going to get my notes out here. One of the cool things that happens Happens in springtime. Oh, how perfect. So I want you to look out for this effect. And I'm going to tell you where and when I've experienced it. So it turns out, I want you to know that sound can also refract, sorry. Even due to differences in the density of the air. So I'll say air density diffs, or differences. So let's go to the Schlachtensee. Ta-da! I love it. Now the Schlachtensee was frozen just a couple weeks ago, so the water is really cold. So don't go swimming unless you're a polar bear. Okay, here's the Schlachtensee. So it's cold. Okay. What that means is in the springtime, now, right above the water, the air is pretty cold. So I'm going to write here cold. Important, Achtung, dense air. If it's colder, the air's not moving so much, right? We learned that in AP Chem too. So it's denser. So cold, dense air. But you know what? It's a sunny day. Maybe not like today, but like yesterday. So what we can get is above this, we can have some warmer air developing. So I'm going to say above here is warm, less dense air. Okay. Here comes the cool part. Have you ever noticed this? If you're standing here and there's somebody else standing here, sometimes when they talk, so we're sending out some sound waves, it's really easy to hear them. And it turns out if it's a springtime, like this is when this mostly happens, at least around here, you're going to get an effect of the sound, okay? And what happens is, just like the light wave with Arga, the spearfisher woman, like the light wave bent in towards the fish when it got into the denser medium, here it bends in as well. So maybe I can make this a little better. So the sound waves go out, but you know what? When they spread and hit this denser area, they turn and go down like this as they hit the cold air here, okay? And this is cold, warm. So as they hit this cold, they change their direction and they bend towards well, in this case, towards the person. It's kind of hard to draw uh, uh, a line here, but essentially it would be a line somewhere coming up here, maybe here, but I'm not going to draw it because it makes it too messy. So the point is, which I think is kind of fun, a refracted sound can travel far. So you could have somebody just having a normal conversation and you might hear them here on the other side. It's weird. I don't know if you've ever noticed that or not. Have any of you ever had that happen? And you're like, wow, why can I hear so well today? Well, it's because of the different densities of the air that the sound is traveling through. Isn't that kind of a cool natural phenomenon? I think so. I hope you have that happen because I find it pretty neat. All right. We're going to skip Snell's law because I can't do the lab with you yet. So let's go right into another application, which is something that you might have experienced. Does it work everywhere? Yes, it does. For example, Anne-Sophie, I could go to New Zealand in the lakes there, and this is going to happen in the fall because that's their spring. So it doesn't happen necessarily at the same time, but it happens in all sorts of places there. And it doesn't have to be a lake, but it does need to be some source of cool air with hot air above it. And by the way, if it's reversed, like here in the fall, if I have warm air and then cool air on the top, sound carries less well. It bends away from, or this way, it bends away from the person, and then they don't hear very well at all. So it's just the opposite when it's the opposite density conditions. And that could well be the case, depending where they were. The other thing, of course, is if the air is more clear, that might be having an effect too, Anne-Sophie. But it could have something to do with density. I don't know the air currents up there very well, though it's a cool spot. Okay, good. Let's go on to a German Fata Morgana. And in English, a mirage. You've probably all seen this, especially if you've been on a hot road in the summertime. And you see the hot road, it almost looks like a mirror. And you're wondering what's going on, okay? Or if you've been in a desert country and you've looked out across the hot sands and there's almost a mirror effect. Turns out, folks, it's not reflection, or is it? It is. No. Hey, I don't like what your book says about this. So I'm going to change to the way I understand it. It's a refraction, is what it's due to. Kind of like with the sound on the lake, but with light. So it's a refraction of light. And let's draw that. This time let's prepare. We are in let's assume we are in an area that has a nice palm tree. So here's your lovely palm tree. Crazy. Remember when we used to travel and we used to see things like palm trees? Try to make my palm a little more convincing. So there's a palm tree. Well, this time it's the opposite effect, depending where you're standing. So what I've got is hot air down here and cool air up above. You know how this happens on a road, right? Because it gets really hot because it's made of asphalt and black and absorbs heat. So I get a really hot road, or the desert sands can get really hot and it's hotter than the air above it. So here's you with your eye. That's you looking. So this time, remember how last time I had the sound go like this? Well, this time it's the opposite. The less dense is here. The cooler air, which is denser on top, causes the light this time, the light rays, to travel this way, and then they travel up again to you. So what you're seeing is it's bending towards the normal when I get into the denser air. So essentially what you see is ironically, you see what looks like a reflection, but it's not. It's actually refraction. So that's sort of the apparent tree. And sometimes you don't really see much of an object. You just see a shininess, right? A shininess. But that's what that shininess is from. It's from refracting air, refracting light rays in the air. So refracting light rays in warm air. So kind of like sound, but just the opposite and the opposite effect. So, and you get to see it, but it looks inverted. It looks upside down. Here's another natural phenomenon. And remember, two things I teach you about physics is all the ideas and where we find them. So for me, it's fun in nature or our own lives where we find physics crop up. So let's answer this question. Why do stars twinkle? Maybe somebody knows this already. So why do stars twinkle, gang? Why aren't they a nice solid light like the moon? Why do stars twinkle? And I don't mean it's because the moon's bigger, okay? What's going on that makes stars twinkle? Let's see some guesses here. Think you folks are awake this morning? So why do stars twinkle? Give you a hint. Yeah, so is our sun, but hint, if you're in outer space, they don't twinkle. Outer space, they don't twinkle. So what's going on? Think of what we're talking about, what our topic is. So let's see. So the twinkling is due to what? Remember, they're really far away. Yeah, they're really far away. Yeah, thank you. Exactly. So the twinkling is due to the faraway starlight. I'll just write starlight refracting. Ellie has it there in our atmosphere. Planets, the light is often a little brighter, so it twinkles less. And the moon, really not at all. It's just too much light, and there's not enough an effect. Yeah, it changes when it changes medium. So refracting in our atmosphere. So we go from here's our atmosphere. We go from no air to the atmosphere, and that's denser, right? Denser atmosphere. So the light, yeah, it refracts there, and that refraction is the twinkling you see when you stare out there. Okay, and it may be refracting more than once, going down through the different layers of the atmosphere. Cool, huh? Okay, now that one you might have known. The next one, before I studied physics, I had no clue about, and I think you'll find it's interesting. It's a good trivia question too. This, I hope, will really blow your minds, as we used to say when I was a pup. Okay, you ready? I'm going to try and draw. Let's see. Let's draw the sun in red. I wish I had a yellow marker. Wish I had yellow, but I don't. So I need a big sun. And I need you to stand like here. So make a little tiny you. All right, you're pretty big if it's that size compared to the Earth, but I'm sorry, this is the Earth. Pardon, the Earth. Sorry. No, not sun, Earth. I should have made it blue. Well, when you look out here, what you see at sunset, you look out and you see the sun. But I'm going to make the sun little dashes. Why? Because that's only the apparent sun. And again, it's because we have an atmosphere. I'm not going to draw that because I want my drawing to be a little less messy. But we'll talk about that in a sec. So outside of Earth, between Earth and Sun, I've got this atmosphere. Yes, I know this is not to scale. The Sun obviously is millions and millions of miles away, but my whiteboard's not that big. The actual Sun, because of our atmosphere, remember our atmosphere is denser. It refracts. And so the actual Sun is down here. This is in effect at sunset and sunrise. I'm looking because I wrote this down better somewhere else. And I want a number. And I don't know if I have that number. I don't. But I'm pretty sure it's a couple minutes. Okay, I digress. Why am I drawing this? Is it just another example of refraction? No, it affects your life a lot of days. Turns out, you know, when you see the sun go down and you see like a beautiful sunset and a red ball going down, well, it turns out the sun has already gone down 2-3 minutes before then. So what that gives us is extra sunlight. So, hey, due to this refraction of sunlight in our atmosphere, we get a couple extra minutes of sun a day. Is it make-believe sun? No, we're getting the rays, but the sun is already down below the horizon. The rays go and they refract back into they refract this way, right? Towards the normal, as it were, although I'm not going to draw that. And they refract into the denser atmosphere. So you see it up here for a couple minutes after the sun's gone down. Isn't that cool? So we get free sunlight every day. Some days you can't see it because it's cloudy. But if you can see it and you see the sun go down, oh, it's going down. But actually, it went down a couple minutes before. If the sun is right above you, there's no effect. okay, because then it's right along the exact line of the normal line, so it doesn't really change anything. The sun goes right at a 90-degree angle. So it's not happening at noon, but the actual sun is slightly down, and it's more so down as you get close to the end of the day. So the maximum of this effect is when we have sunset or sunrise. And I think if I understand the effect right, when you see the sunrise, it hasn't risen yet. You know what I'm saying? You see it, but it's still a little bit below the horizon, but you're seeing the refracted rays coming up, right? As it were, coming up. I know it's not coming up, but from our point of view. So at any rate, exactly, our atmosphere provides a change in medium, and that's what does this weird extra effect of extra minutes of sun due to refraction every day. Yeah. So I hope you find that fun. That's one of my favorite little weird facts about refraction. Okay. Good. If you got a question, let me know. We're going to go back to water for a moment. I think I told you this yesterday, but let's just kind of find out. So if I got some water, and if I've got a flashlight, an underwater flashlight, if I shine it up, then it's going to go, and it's going to go away from the medium like this, right? And if I move it over, oh God, I kind of wrote the word flashlight right where I want to put that, but anyway. If I do my flashlight over here, and again, it refracts, it refracts away from the going into air. I just got to think about it. Sorry, I'm hemming and hawing. And I might be overemphasizing it, but it refracts away here from that. That's probably less. And this is probably more. But you know what? Here's the deal. So it's for sunrise, sunset. It should add 2 minutes difference. Thank you very much, Anne-Sophie. Appreciate that. Isn't Google great? Although I like it less when I'm wrong, but often I'm right. Thank you, Anne-Sophie. Okay, so here we go. Turns out if I shine a flashlight up, you might notice this, and again, I got a nice demo at school where I can't be right now. Some of the light refracts. Well, some of the light actually reflects. So I get a little beam of light going like this. And I'll write here, some reflects. So all the light doesn't do the same thing. Well, it turns out once I get to an angle, and we talked about this last time, but it was a little rushed. I'm going to bend my flashlight over more now and shine a light and extend my water a bit. If I hit this magic angle, I got 48, but I'm pretty sure it's 46. All right. I'll have to look it up in the book. Sorry. Bad teacher. If it's right, then I told you the wrong number yesterday. Let's find out. Okay, so turns out at a certain angle, it doesn't go out anymore. It simply all reflects. And what we call this, folks, is complete internal reflectance. And it's important because we're going to use it for some stuff that's actually going on in our school. Okay? So this is now complete internal reflectance. All right, and I've got 48, so I might have told you the wrong number yesterday. Dagnabbit, let's just find out. You could probably look it up quicker than me. So the angle of complete internal reflectance for water is what? Is it really 48? Or did I screw up? And I cannot find it. I cannot find it. Ah, no, it's going to be in here. All right, good. That is 48. Doggone it. Okay, so I told you the wrong number yesterday. It says 42 in my book, and I don't think that's changed over time. It says 48. Make sure that when the flashlight is tipped beyond the critical angle, 48 degrees from the normal in water. Let's go with 48. So what that is this angle here. And it's called the critical angle. Critical angle. So what I need you to know is, hey, if I go beyond the critical, so at or beyond the critical angle, all light reflects. So this critical angle is pretty critical, and it has some cool applications in the world. So the first one is our fish diagram. So I might have given you the wrong number. Thank you, Ellie. So 48, 49. So the wrong number, if I told you yesterday it was, I don't know, 92 or something, it's obviously double 48. And if I look up as a fish, I won't see 180, I'll see double 48, which would be 90, 96 instead of 92. So that's my horizon if you're a fish. If you're underwater, you see it as a 92 degrees like this, and you see like this circle of light. And beyond there, all the light reflects. So beyond there, if I go beyond there, it just keeps reflecting, okay? So if I go more here, it just reflects. And it looks like a mirror if you're in the pool looking up. Thank you, Ellie, for looking at that and finding that for me. Well, this is all sort of interesting if you're a fish, but why should I care about it? Well, there's some cool applications. Light, its critical angle is 48 degrees or 49 if Ellie's got it there. Here's another application. Diamonds critical angle equals 24.6 degrees. That's really low. So what does that mean about diamonds? Here's a diamond. I'm going to draw a really crappy diamond. You ready? What that means is diamonds, if light comes in, the light tends to do this. Oh, um, it's a greater angle here, so it just all reflects, reflects, reflects. Oh, maybe it comes out here. Or sometimes it goes in, I'll do another color, and it might sort of reflect like this, like this, like this. Maybe some of it comes out here. Okay, what's my point? My point is that the angle is so low that a lot of light in a diamond stays in the diamond for a while, bounces around, and comes out weird sides. Let me try and write that. So light bounces around in a diamond before coming out some face of the diamond, face or facet, if you like the diamond official language. Let's just call it a face of the diamond. That's why diamonds do what? They sparkle. So what the sparkle is for diamond is it's really the light coming out in odd places. So if you have a diamond or one of your parents does in a ring or something, see if you can borrow it and look at it really close if your eyes are good and move it in the light and you're going to see some light come out in funny spots because it's reflecting internally and then coming out at other faces because its angle of reflectance is so flippin' low. So diamonds are special in that respect. You can buy fake diamonds, but they don't do that quite as well, like zirconium, whatever, okay? Its critical angle is low, but it's not as low as a diamond, so they don't sparkle as much as a diamond does. So there ain't nothing like a diamond. They're not as hard as a diamond either, but that's something else. Okay, then our last application for reflectance, refraction, is something called fiber optics. You probably know all about this. I have this at school. If I think of it Tuesday, I'm going to show you some fiber optics cables. They look like fishing line, okay? So it has a, let me make sure of it before I say it. Yeah, they have a low, well, fiber optics are, it's basically a type of glass, not fiberglass. Okay, let's just call it plastic. So these are made of a flexible plastic where light shining in stays reflecting. So it's got a low critical angle. So here's what it looks like. Okay, what you do is you shine light in here. Okay, here's your light. And the light, even if I shine it at an angle, it doesn't really matter. It bounces off like this. And it stays in here. And it just keeps going. Clever people about 30 years ago decided they could use this for high-speed communication. So your voices, your computer data is changed to a form of light, and then the light is sent through fiber optics cables, and I can send a lot of data through fiber optics cables. Years ago, they used to use copper wires. They can't send much through a copper wire. They can send infinitely more through these fiber optics cables. So they used to have copper wires this big around, right? Now, fiber optics like maybe this big, okay? And we just got, I know it's 2021, but we just got hooked up this last few months with fiber optics cables in our school, JFKS, to try and beef up our internet Wi-Fi. So hold on to your seats. After 100,000 years at the Kennedy School, we might get better internet after they hook it up, which is supposed to be Easter break. Isn't that cool? So fiber optics is now used for communication. So fiber optics used to send, I'll just say data. And the data is encoded, put into code, encoded into light. Encoded as light. And obviously on the other end, if it's like a phone conversation or something, it has to be decoded, and the electronics do that, and so you can hear someone again or see the data or whatever it is. So turns out the fiber, and again, it looks like fishing line. You look at it, and it's not hollow. It's solid. It's solid. Okay. So the fiber, these are like solid plastic wires. So if I think of it, I'll get one out and we can play with them. We can play with them when I see you in school next week. I hope that will be the case. Whoa, that's a lot of applications. Questions from you so far on all this. It's not new technology, but it's technology I wanted you to know about, how we use it. Okay, while you're thinking, I'm going to go back, talk a little bit about this. At least I think I will. Yeah, 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 yep, 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 yep. That's where I want to be. Okay? It's how that's one way to determine if it's a real diamond. And that's the safe way, Anne-Sophie. Uh, they will check and see, they'll measure what's called the critical angle. They'll use what's called Snell's law, which we've done a lab in some years, probably won't this year. They'll check that angle in the diamond. Now you could say, but a diamond is a lot harder. Can't they just take the diamond and scratch it on something? Well, they can if they want to screw up the diamond possibly too. So you could scratch the diamond on something to check its hardness, but people don't do that because they don't want to harm the diamond inadvertently in any way. All right. So probably, Anne-Sophie, they're going to use your method and actually measure it under an optical scope and look at its critical angle and see if it is indeed 24.6 degrees or thereabouts. Yeah, good question. Any other questions from you about diamonds or fiber optics and so on? There's a lot of physics in our lives, huh? We don't even think about it, but it's there. It's there all the time. And especially in our next topic. You ready? Let's talk color. If you want to know where I am in the book, by the way, this is chapter 28. There's actually some nice pictures there, things I can't draw. Some of this you know. Black objects. White objects. All. So can you pick one, black or white, everybody? Type in the answer for the blanks. Black objects, all, White objects, all, Help me fill those suckers in. What do black objects do? What do white objects do? In fact, I'm wearing both. I have a black outer thing that's doing something with the light right now, and I have a white inner thing with the periodic table on it, of course, that is doing something if I show that. And thank you. Yes, Ellie, good. They absorb all light, the black ones. And the white exactly reflects all light. So to be really honest, black's a good color to wear in winter. So winter, black stuff gets warmer. And of course, summer, white stuff stays cooler. You probably knew that already, but that's why, isn't it? So a lot of countries wear a lot of white in the summertime because it does reflect the light, especially some desert areas, okay? Makes a lot of sense. Do you know about polar bears? Shouldn't they be black? They are. What's the deal with polar bears? Anybody know for fun? It's a bit like they're covered with fiber optic hair. So the hair is dark. The skin is dark. Believe it or not, have dark skin. Their hair guides in the light and takes it like a fiber optic cable to the dark skin where the energy is absorbed. Ha! So not only does it help insulate them, because that's what hair does, it helps take the light right into where the skin is. Their hair guides light to be absorbed by dark skin. They are smart critters, except for that whole global warming thing. Poor things. Seriously. I'll say, of course, and they're insulated. We know that too. I don't want to tell you that that's all that is. So the hairs help insulate the bear as well. But they also guide that light like a fiber optic cable, but not made of the same stuff, to the dark skin where it's absorbed. The light is absorbed there and warms up the bear. Beautiful. Bears know it. Bears know what's going on. Okay, other colors are kind of a mix of black and white. Let's take red. When you see red, there's some red. What happens is, it means what? If you think about it, all the light is absorbed by the red dye. For the AP people and Sophia and Ellie, it's absorbed by the pigment molecules. They absorb the energy. They absorb the energy. So all light is absorbed by red dye except red, which is re-emitted. I don't want to say it like reflects off, but is re-emitted. What is re-emittance? Well, reflectance would be like this, right? That's not happening. Re-emittance is like this. Okay, I catch the light, I'm red, and I'm going to throw it back now. So I'm going to catch the light, I'm going to absorb all the other colors, but I'm going to throw back red. That's re-emitting. So it's absorbing the other stuff, throwing back the red. Or blue, right? Blue absorbs the other stuff, throws back the blue, re-emits the blue. So that's what color does. So if you're wearing a green t-shirt, you're absorbing everything except for green. Apropos, chlorophyll. You know this from bio class, right? Chlorophyll is green. Chlorophyll is a cool, not cool as in cold, but pretty neat molecule. Absorbs all color except fairly low energy green. So it accepts a lot of energy. And you know from bio, right? It takes in the CO2 and H2O with that chlorophyll molecule, with that energy from the sun, energy absorbed here by the chlorophyll molecule, everything except a low energy green, and then converts it to sugar. But you knew that already from bio. I don't have to write that. But that's physics taken, to the bio application, right? A little chemistry too. Physics, chem, bio, they're all like brothers and sisters, you know? Do I want to do that? No, I don't. Not this year. Not this year. Pigments in skin absorb some, I'm going to write wavelength here, lambda. And of course, for clothing, it's dyes. So it's something added to the clothing. So when you order clothes, you're ordering something they've used a certain pigment to absorb or reflect, a certain molecule to absorb or reflect different colors. In our skin, depending on who we are, same thing. Some wavelengths are absorbed, others are not. Okay. Okay. That's a good spot to stop. I'm going to think about what we want to know about color next time, tomorrow. So I will have class with you tomorrow. And then we'll be back live next week. So I'll see you on Tuesday, but I will see you live. I'll see you virtually tomorrow. So I wish you a good rest of your day. Write me if you got questions on anything, and try and finish up the earthquake questions for me. Okay? So be good, be healthy, and we'll see you tomorrow. Bye, gang.